So good evening, ladies and gentlemen. I'd like to welcome you all here this evening. This is the last evening lecture of the Energy and Environment Division 2015-2016 series. So we'd like to welcome the people attending by webcast, including a group who have convened in the Energy Research Institute in UCC. So the lecture this evening is a joint event between Engineers Ireland and the Energy Institute and the Cork region and Energy Cork. So the lecture this evening is the subject of the lecture this evening is power system inertia, the challenges and solutions. So the synchronous generator has long been the backbone of the power system since its creation, simultaneously providing both energy and ancillary services. So worldwide synchronous inertia is in decline as more renewable asynchronous generation comes online, i.e. wind turbines and solar PV. And this has generated a requirement for a new range of ancillary services and technologies, and indeed a new approach to system inertia. So as people will be aware, there's a lot of information and indeed misinformation floating around on this topic. And I think this evening is a chance, for the Engineers Ireland to bring a bit of, rigorous engineering analysis to this topic. And our speaker here this evening is Padraig Daly, who is a PhD student in the School of Electrical and Electronic Engineering at UCD. He's currently researching bridging the gap between power system stability and scheduling high levels of renewable power in the system, with a focus on the creation of implementable research outcomes. So without further ado, I'd like to hand over to Padraig. Thank
you. Thanks very much for coming, taking time out on a nice afternoon. Hello to the people in Cork. Apologise if I wander off screen and get excited with my slides for a second, but I'll come back. Today I want to give an overview of power system inertia. We'll start off quite basic for everybody, talk about kind of the fundamentals of the problem, the importance, why are we declining from an inertial perspective, and then go through some solutions that we've developed in UCD and elsewhere, what's going on in the world. So to start off, I'm going to bring you back to your secondary school physics class, and that equation that you've seen before. Kinetic energy is half times the mass multiplied by the velocity squared. Now this term for kinetic energy can be mapped to the rotational frame, which is what we're interested in when it comes to conventional synchronous generators rotating when they're connected to the grid. And an analogous equation for kinetic energy in the linear time frame is rotational energy, which is a half times the moment of inertia times angular velocity. So we can see that the moment of inertia is taking the role of the mass, and the angular velocity, the rotational speed, is taking the role of velocity in a linear frame. And this rotational energy is what is colloquially termed as inertia. This is when people say inertia, they're really talking about the rotational energy of a synchronous machine rotating once connected to the grid. Why is it important, or why do we care? So we know, okay, we have energy. What does that all mean? Well, this is a simplified schematic of a synchronous generator, and the speed of rotation of the shaft is directly coupled to the frequency of current and voltage injection into the grid. So what that means is that the mechanical speed of this machine is umbilically linked to the grid frequency, the electrical speed of the system. If we drop back to our equation, we know that the angular velocity is related to the rotational energy of the machine. So this angular velocity, which is connected to the grid frequency, so if the grid frequency changes, that angular velocity term will change, and hence we have a transfer of rotational energy to or from the grid depending on which way the frequency changes. this is like, this is just a consequence of, I suppose, the beauty of the design of a synchronous machine. It's pure physics. Now, I suppose not all power plants are created equal when we come to inertia. So to give you a feel for, the power systems are diverse, and so are the inertial sources. So here we have a coal plant. Typically, they have a stored energy of 1,500 megawatt seconds. I'll put that number in context in a minute. I just want to compare at the moment. This is a combined cycle gas turbine, probably the most popular technology on the Irish system at the moment. You're looking at around 3,000 megawatt seconds typically. Nuclear plant, which we don't have in Ireland, they're typically higher again, 4,000 megawatt seconds. And then a little peaker, little open cycle gas turbine comes in at a trusty 200 megawatt seconds. Now, these are all different for different reasons. And it's because of this, so this equation here defines the stored rotational energy. That W rotational, that's the stored energy of a plant, and that's equal to the inertial constant multiplied by the apparent power rating. The apparent power rating is just your electrical size of the machine. And the reason I throw up this equation is because the reason that a nuclear plant is on average heavier than a CCT is because it has such a great electrical size. You're talking about 1,000 MVA for a nuclear plant, but its inertia constant is lower than a CCT. You're talking 500 MVA for a combined cycle gas turbine, but its inertial constant is up at least 6 for single shaft. For double shaft CCT, that goes higher again. So these plants are range for different reasons. To put, I suppose, just to bring it back down to the normal day, this is a brand new turbine from Alstom. When that's rotating at synchronous speed, let's say assume we have that 3,000 megawatt seconds, that stored energy is roughly Mr. Bean on his Mini moving at 30 kilometers an hour, including mop, Mr. Bean and the chair. So that kind of gives you a feel for how much energy we're talking about. So then we move on to our new technologies. PV has no rotating mass, hence it has no stored energy. Okay, simple as that. Now, wind turbines do have a stored energy because they have a rotating mass. Those blades are turning. Now, it's probably a bit of an unfair comparison, to be honest, because one wind turbine it's a small MVA. You're going to have thousands of wind turbines on your system, so when you aggregate that stored energy will be much higher. Except there's a caveat. Wind turbines are generally not synchronously connected to the system. They're non-synchronously connected, and what that means by non-synchronous connection is that it's electrically connected to the power system through power electronic devices. And the reason manufacturers do this is because the wind speed is variable. So in order to harness or capture the most amount of energy from the wind when the wind is moving, the machine will change its rotational speed to match the wind and harvest as much energy as possible. So this is the culprit, I suppose. That red box there, that's your power converter that decouples the speed of the generator with the grid frequency. So, okay, if you're believing me so far, synchronous inertia, the new sources are less than before. But why do we care? Like, what's it all about? So as an example, I'm going to take the US power systems. So there's three. There's the Western interconnection, Texas on their own, and then the Eastern interconnection. And you can see that Eastern is bigger than Western, and Western is much bigger than Texas. Okay, so they've different loads, so they're going to have a different number of generators online to meet that load. So the Eastern interconnection has greater inertia than the Western, which is greater inertia than Texas. So here's the frequency response of the three systems. In blue you have the Eastern interconnection. You can see that the rate at which this frequency falls is less than the Western interconnection, which is less than Texas. That's because the inertia of a power system, the rate at which the frequency falls, is directly proportional to the inertia on the grid. So you can see that the more inertia you have on the grid, the slower the frequency falls, and as a consequence, you're less likely to get in trouble. Now, these rates of change, that initial slope, that's what the inertia governs, okay? So these different characteristics along here, that's a different response time frame, okay? When I'm talking about the inertial time frame, I'm talking about between 0 and 3 seconds following a disturbance on the grid, okay? So this will run out for up to minutes, and these characteristics are different. For example, in the Eastern interconnection, a lot of generators lock their governors. They lock the control because they're not paid. They're not mandated or paid or incentivized to have that control, so they lock it. And that's why you get that lazy L shape on the Eastern interconnection, even though it's got a heavier inertia. So I suppose there you can see already that economics is driving the technical response of a power system. So that's from a system perspective. Okay, so now I'm saying, okay, the frequency falls at a greater rate. Why do I care about that? Well, like any set of machines, power plants are built for an optimal speed and optimal operation. So there's consequences for having extreme frequency excursions, and that's why the system operator wants to have inertia on the system, because it will guard against you getting into those extreme territories. So one example here, this is a simplified schematic of a combined cycle gas turbine. And the combined cycle gas turbine operates a lean fuel mix. And what that means is, on a simplistic level, there tends to be more air than fuel when it comes to that ratio. Now, when the frequency changes, let's say, for an example, we have a short circuit fault in the system. When you have a fault on the system, your voltages are suppressed, okay? And that means that the electrical power output of a generator cannot be shipped out. So because you cannot get all that mechanical power through the generator and out into the system, the machine starts to speed up because the mechanical power input to the generator is greater than the electrical power output. Now when that happens, because all these shafts are connected to the grid frequency starts to rise, okay? Now that air is compressed, and that compressor, that has a speed which is linked to the frequency. So if the frequency is rising because of this short circuit fault, all of a sudden the compressor speeds up and we have more air coming in. So all of a sudden we're getting leaner. Now what controls the gas flow? That's the governor. So if the frequency rises, the governor is going to respond to that and pull back the fuel. So all of a sudden we're getting leaner again. And if that gets too extreme, you can have a lean blowout, and the gas turbine will trip off as a result. So as an illustration of that, what I'm going to show you is an event in Florida. So this happened back in 2006. So I suppose the things I want to look out for is there's a fault on the system in Florida. The frequency rises. Because of this lean blowout, the gas turbines disconnect. So all of a sudden we have a generation consumption imbalance. The frequency falls. And you'll see the results to the network frequencies all around the US grid. Suppose I should have put in some motivational music behind that or something, but. This is the US, so it's 60 hertz. We're 50 over here. Okay.
What band do they guarantee on to the purchaser? In frequency, is it 59 to 61 or is it wider?
It'll depend from system to system. So in every grid code for a power system.
Here.
On the US, I'm not particularly sure. It will be. It should be with outside that range.
Yeah, so that's within it.
Yes, yeah. But there's always unintended consequences, for designs and stuff like that. So that's conventional plant tripping. Another aspect that's coming is distributed generation tripping as well from extreme frequencies. And what I mean by distributed generation, I mean generators connected to the low voltage system, the distribution system. So that can be wind turbines, solar PV, combined heat and power. They're the main three, typically. And these generators, because they're connected on the low voltage system and they're close to you and me where we live, they have protection systems that will trip in case there's an island in that region to protect us all. But often what happens as well, the way they detect that island is from rate of change of frequency that they measure, and also under and over frequency levels that they measure. So sometimes there can be an event on the system, and these protection system on the generation or the distributed generation can maltrip. Now, if you make them less sensitive, then they mightn't actually detect the thing they're trying to guard against in the first place. So there's a balance there. So I'm not sure if you've heard before, but in Germany and throughout Europe, I think it was called the 50.2 hertz phenomenon. So all the PV that was installed, their settings said, okay, if you go to 50.2 hertz, trip me off. And this is okay in small penetrations, but when you get to high penetrations of distributed generation, again, you can have these unintended consequences. So what I'm going to show you is a trip of 2 gigawatts of interconnection in Europe and the resulting frequency response due to the cascade tripping of distributed generation. So you can see you lose the cable, the frequency increases. At 50.2, you have a cut of solar panels, and because there was such a high penetration of well, this is simulation, but because there's a high penetration of PV, the frequency falls significantly. And as you go through the different thresholds, you have different types of distributed generation tripping offline. Now, they've come up with countermeasures since by changing the settings on the distribution. But again, it's just another consequence of extreme frequencies.
How does the frequency go back up if there's no generators on air?
Sorry?
How does the frequency go back up?
So right at the end, there's load shedding. So there's involuntary customers shedded at that point to make the balance back up.
So you presume people are being signaled to switch off certain loads?
No, you're shut. Unless you're a hospital, you're coming off. There'll be a blackout so every power system in the world will have load shedding, and it's kind of the goal of the TSO to make sure that doesn't happen in an economic fashion. Last one I'm going to talk about is steam turbine blade damage. So if you have extreme frequencies, you can actually get resonance in the blades because everything has a natural frequency. So as you can see that now these are massive changes. You never really see these, but I think it's good to show that as the frequency gets more and more degraded, you have less and less time that you can operate the machine. It's just a transmission line has the exact same impacts if it's overloaded. The reason is because once you move away from the nominal frequency, the stress amplitude increases, okay, and you can get degradation on the blade. Okay, so this is the Norwegian Pearl, and this is, I suppose, one of the last things I'll talk about before I get into some research. The Norwegian Pearl wanted to go to the Black Sea, so there was to do so to go through the passage. You had to switch out an overhead line, and there was a small bit of miscommunication between the TSOs in Europe. This guy rocked up 3 hours earlier than they anticipated, and they had done N-1 contingency analysis each TSO, but at 3 hours later, not 3 hours before. And once they disconnected this line, surrounding lines got overloaded, and you had a cascade tripping of transmission lines throughout Europe. And what happened was that the European grid, I suppose the point of this graph is to show it ain't just small systems like Ireland for which inertia matters. The European grid split into three. three regions, and there's the accompanying frequency response. Okay, so I suppose going forward, actually, Ireland is small, so I'm not sure it'll matter. Maybe if you want to prevent system splitting between Northern Ireland and Ireland, but the location of the inertia might matter in the future as well. Okay, so getting into our own work in UCD, I'm just going to try and characterize what happens in a low inertia power system. So if you increase the penetration of wind or PV, okay, they've two important characteristics when it comes to unit commitment and when you scheduling the system at least cost and frequency stability. One, there's zero marginal cost. So once you give that to a cost optimization, it's going to take that free resource of energy, and then two, it's non-synchronous. So they're going to displace conventional generation purely out of economics, okay? So what I'm showing here is a duration curve. So this is the cumulative probability that the system inertia will be above a certain level. So what I'm showing you is an installed capacity of 2 gigawatt seconds. You can see then if we move to 4.5 gigawatt installed capacity, the inertia of the system reduces significantly. And then something that's also most likely going to happen in the future is that demand response is going to start offering operating reserve as well. And that's a non-synchronous technology. So if we're getting our energy and reserve provided by non-synchronous sources, the inertia is going to fall even more. So inertia is falling. We need to start monitoring it. So we do it here, but they also do it in the Nordic system, and that in the control room, they monitor the inertia of the system. Now this is just the sum of the generators. The inertia will have the load will have an inertia as well. But you could argue with data centers and modern motors having variable frequency drives that the inertia of the load is going to disappear. So I suppose just an example there, Sweden's up at close to 100,000 megawatt seconds. That's because it has plenty of nuclear plant. Norway's pretty high as well because it has hydro generators. Interesting thing actually is that Brazil are starting to get worried about inertia, I'm told, and that's because the latest hydro generators are lighter than the previous generation. Okay, so I suppose inertia is falling again. Why do we matter? So we're going to talk about what's the impact of a degrading of lower inertia on system frequency response. So it has a direct impact on two things. So it has the rate of change of frequency. So this is a probability distribution function of what your rate of change of frequency will be if you lose the largest generator on your system for every hour in the year. Okay, so all I want you to get here is that as the wind penetration increases, that curve is pushed to the right. That's pushed to more extreme rate of change of frequencies, okay? The other thing that has a direct impact on is the time to maximum frequency deviation. So because we're falling faster, okay, we're hitting our minimum frequency in a shorter time frame. Okay, so you can see we're coming back to shorter time frames. So basically we need to act. As inertia falls lower, we need to act on a faster time. Okay. But I suppose it is a bit of a tad simplification to say that, well, okay, we know that higher wind penetrations lead to lower inertia. It's not correct to say that higher wind penetrations lead to higher rock-off, okay? Because there's two parts to the rock-off equation. There's the size of the size of the contingency, and also the inertia that you have online. And what can happen sometimes is at higher wind penetrations, your largest in-feed is not as big as it was at lower wind penetrations. So you need to be careful about how you might go, to guard against rate of change of frequencies rock-off, you need to characterize it. So what I'm going to show you is a scatter plot, and each dot represents a simulation. So it's the loss of a contingency. And what I've done is I've looked at the inertia online and the size of the generator that was lost in that instance. So you can see, and this is for in-feeds, so it's a generator or a HVDC import. So it's a negative rate of change of frequency. So you can see that there's two things at play. As the contingency increases, we get extreme rock-offs, and also as the inertia declines from red to light blue to dark blue to green, we get more extreme behavior here as well. But of course, you can also lose an interconnector on export, or you could lose a large load. So what I'm showing here is instances where we actually lose an interconnector. And these actually occur during low inertia times, because generally we import to Britain, you know, that's totally defined by the change in the relative price between the two systems. And when we have high wind at night, we can start becoming competitive with the Great Britain price. It's a bigger system, so it generally has a lower marginal price of electricity, but when our wind penetrations get up, we can start exporting. So we're actually, we can be, although there's a less number, you could argue that the risk is higher. So you could also try and categorize the risk of rate of change of frequency by time of day. So what I'm showing here is the probability for each hour, so from 1 to 24 on average, of a loss of in-feed. And what you can see is that the two different colors there, so for a band of rock-offs between 0 and 0.5, and then from 0.5 above. And you can see that the risk doesn't really change throughout the day. It's quite constant. Okay. Now, if you contrast that with over-frequency events for loss of interconnector, we can see that the risk is much higher during the nighttime. Okay, because that's when we export. So you can see we start importing then during the day, and this risk falls off. So you can see, I suppose, there's an asymmetry here that we need to guard against different things at different times. So that's the label. Traditionally, because unit commitment is such a computationally intensive problem, it's a mixed inertia programming problem. It has binary variables involved. Generally, the constraints are quite simple. And in a world when there was no renewable generation, and we just had power plants, fossil fuel power plants, providing both the energy and the ancillary service that the grid needs for reliability, what you could do is you could constrain on generators. You could say, okay, you're a must run. You have to be on at all times. And you could do that for a host of reasons. You could do it for voltage control. You could do it for short circuit power in a weak part of the grid. You could do it for inertia. But the problem is, like I said, higher wind penetration does not necessarily lead to higher rock-off. And in a similar fashion, just because you have more generators online doesn't mean that you'll have a lower rock-off. There's so many operational conditions involved with having a certain number of generators online, because the wind level is changing, the demand level is changing, imports, outports. So what I did was I tried to characterize, okay, how robust is a must-run constraint for rock-off? So what you have here is the initial rate of change of frequency as a function of the number of large conventional units online. And you can see that there's a huge variation for a given number. So let's take 8 units online. You can go between 0.5 hertz per second all the way up to 0.7 hertz per second for that given number. So I suppose we know the problem, and we're searching around for solutions now, and this was one that, although traditionally quite popular, I'm not sure if this is going to work going into the future. Another alternative you could have is a synchronous condenser. So what a synchronous condenser is, it's a synchronous machine without a turbine. So it can't create energy. But what it can do, once synced to the grid, can provide voltage support and fault current. And inertia, because now, albeit less than a power plant because you don't have the turbine anymore, but there's still the inertia of the synchronous machine once synced to the grid. Now, the leaders in synchronous condensers are EnergyNet in Denmark. The purple dots there are the TSO-owned synchronous condensers, and the green ones are independents. And the reason this came about was because the Nordic market sets the generator dispatches. But what was happening was there wasn't enough controllability on the system to maintain your voltages. So what the operator had to do was to go out of the market, go out of merit, and ask a generator to turn on so that it could provide ancillary services. But of course, a power plant wants to produce energy. That's what it gets paid for most. But the operator only wanted to turn on a minimum load. So the power plant owner said, pay me by the hour, because I'm not getting enough energy money. And all of a sudden, the must run, the out of merit costs for running the Danish grid was unacceptable from, in EnergyNet's own words. Must run is too costly, they say. So what they did was they've procured 3 synchronous condensers in the last number of years, so that they don't have to go out and buy these ancillary services out of the merit. They're network installations that they have control over, just like we have our interconnector here.
Is this a road for UPS?
Hmm?
It's like a road for UPS.
No, because a synchronous condenser is a synchronous machine, so it has rotating mass, and it's not only that, like the source of energy, you could argue doesn't matter, but it's directly coupled to the grid frequency. So when the frequency falls, it will inherently inject its stored energy to the grid. Well, it'll slow down, and because it slows down, it injects its stored energy. The thing with a UPS is like synthetic control of a wind turbine, in that it's not directly coupled to the grid. I'll get on to that in a sec.
What kind of power would a synchronous condenser consume?
It's about 3% of rated capacity. Now that will change if it's idling. It depends how much on the reactive power production of the unit as well. But roughly 3% of the MVA.
What is the rated capacity for the ones that are?
They're 270 MVA, so they're quite big. They actually have the EnergyNet don't really have inertial problems because they're connected to the European grid, which is quite big. A grid, the power system doesn't act by country; it acts by who you're synchronously connected to. So the European system is one grid, and they're connected to the rest of Germany and France and whatever. So they don't have they bought these for voltage control reasons, but you could map it to Ireland for inertial reasons and voltage. I suppose that's the ideal scenario with a technology. It can provide you more than one ancillary service, because if you're banking on one ancillary service, you mightn't make enough money back. So I'm going to quickly go through our own formulation in UCD. So we've devised an inertial constraint within unit commitment. Quick peek of it there. I don't want you to get too worried about it. All you do is you define your rate of change of frequency that you're worried about. What the constraint does is it'll modulate, or it'll dynamically change the inertia of the grid to meet whatever requirement you set. Now the thing is that it changes with each time step. So So at every point it will see, okay, what's my contingency? What do I need? And then it will optimally choose the binding contingency and the sum of the inertial constants from, or the sum of the inertial provisions from the units to make sure that you're within the rock-off limit that you set. The really nice thing about this constraint, it's a linear approximation, and what that means is that, so every power plant, or a protection device will be reading the frequency. They have to measure the frequency from the grid to know that, oh God, the rate of change of frequency is above a certain threshold. Okay? And that's done over a certain window. If anybody ever talks about rate of change of frequency, the question you ask back is over what time frame, okay? Because that it doesn't mean anything unless it's over a certain time frame. Same with moment of inertia. About what axis are you talking about? Because the answer changes if it's a different measurement window. Okay, but because this is a linear approximation that we have here, it means that it's always going to be the worst case scenario. So what it means is that the constraint is going to bind for a limit that's slightly, it sees a rock off that's slightly greater than what the protection settings would see over 500 milliseconds. So within this constraint, there's an inherent safety factor, which increases as the rock off increases. So there's kind of like an inherent engineering safety factor due to the linearization. And then quickly go to, again, you don't need to worry about the cost numbers here. So what we've done is we've just compared different inertial strategies for a high wind power system. So there's the cost if you've no inertia. If you do what I said at the start and you say, okay, I want 8 generators online at all times, obviously there's going to be times where there's less than 8 units online, and then you have to constrain those units on, so your costs are going to increase. An alternative strategy would be to say, okay, I want a minimum amount of inertia online at all times. I don't care what the large thin feed is, if it changes, if it goes below what I'm setting it. I want to be safe with that number at all times. When that happens, the costs do increase significantly for that associated level of robustness. And then for our interval, our time step dependent constraint, we can guarantee a greater level of short-term of inertial response, a better inertial response than this case, while also saving you money. Okay, for time. Okay, we're not too bad. So that's conventional generation. At the moment, that's typically fossil fuel fired. So there's a carbon footprint associated with that. So you might move towards wind turbines and see how could you control that technology to help your system frequency response. Now, this is different than synchronous inertial response. Okay, don't have anyone tell you they're the same thing. So what's going on here is this is the inertia, the emulated inertial injection of a wind turbine to a contingency. The reason that there's different plots here is that the stored energy of a machine depends on its rotational speed. So throughout a system, you'll have wind turbines rotating at different speeds because the wind conditions are different. So in order to model this properly, you need to have a couple of wind models to get an accurate representation of what's actually going on in the system. So you can see that the recovery of the wind turbine changes with wind speed. Now I'm going to contrast that with a synchronous inertial response. So this is a CCGT and a coal-fired unit. I suppose the two things to note is that this moves. This is umbilically linked to the frequency, as I said. So this is related to the rate of change, so the DFTT of the frequency. So this will move automatically with the system frequency, whereas this response here is decoupled from the frequency. Whatever the grid is, that's more or less what you're going to get. And just, I suppose, to hammer the point home, this is the equation that describes, again, I don't want you to get worried about it, but this is the equation that describes the inertial response, or the power injection of a conventional generator, okay? This is the equation that describes how you control a wind turbine to get and emulate it, a somewhat like inertial response from a wind turbine. But because you can tune this now, you have the keys in a sense, and that you can't control this, you can't change this, but you can tune these parameters to meet your system needs, albeit slower than the synchronous inertial response. So because it's a controlled response, it'll do what you tell it to do. And as a result, you need to be very careful with how you set those parameters. So what I'm showing here is the frequency response of a system and how that changes with how you change the parameters of your wind turbine controls. So if you ask for a very high, the red one there, a very aggressive initial response from all your wind turbines, you're slowing down all the turbines, you're injecting power, but the machines have to speed back up. Okay, so a wind turbine is on a max power point tracking curve. It will move so that it extracts as much energy from the wind as the wind speed changes. Now, after an event, the inertial controls kick in, and then once that injection is given, it'll hop back onto the max power point tracking curve, and then you have the machine speeding back up. So that's why you have this withdrawal of energy. It happens with a synchronous machine as well, except in a synchronous machine it's in unison with the system frequency. So when you get a very aggressive initial response, that red line there, what happens is that the system frequency is nadir, or minimum, is formed. But because you've asked for so much, the recovery is quite great, and the frequency falls then again. Likewise, if you ask for it, you can. So that's the gain. That's the of the machine. Likewise, you can control the how quickly and how long it responds for with these time constants. So if you ask for a longer response, that also will hurt the system frequency, and you can see this decay here. I suppose what I'm trying to say is that this is roughly 5 seconds, so a governor response is coming up by now. So you don't particularly want the wind turbine to be continue giving you something there, because other sources are kicking in. You want to give it a high initial injection, but not too aggressive. So I suppose you get this moderate. That black curve is what I'm going to call a tuned response. Now that's just one case. So what I've done here is
Does this mean that a wind turbine, because of the inverter, can actually simulate a very high inertia compared to its size? Because it can generate whatever frequency it wants to, or whatever speed it wants to.
No, in that there's the source of energy is still finite. Like, it's still the only reason that you can call a wind turbine emulated inertia, in my view, is because the source of the energy is still the rotational energy of the machine. It's still what we call inertia. Now, it's synthetic, but so a wind turbine, it like anything else has a limited amount of energy. So that's all that you can extract. What you need to be careful about wind turbines is the nature of the extraction. How long do you want to extend that for? Because there's consequences involved. But if it's tuned, if with any control device, if it's tuned correctly, it should help the system. Okay, and what I'm comparing here, the blue, that's so this again the full year scenario. So this is like 8,000 simulations each. The dashed blue line there is the mean system frequency without emulated inertial response from wind turbines, and the black is the mean system frequency of all those cases with a tuned emulated inertial response from wind. And the boundary there, those shaded parameters, that's the standard deviation of the response, just to give you a feel for the rest of the simulations in terms of where are we moving. I suppose points to note, that maximum rate of change of frequency wasn't impacted, but what it can do is that it can minimize the deviation. What these controls can also do is it can actually push out your time to nadir. So for example, if you compare the blue and the black there, you can, with these controls, you can push out that time to minimum frequency as well. I suppose these are my lovely simulations rather than the real world. So Hydro-Quebec in Canada actually have a grid code requirement for all wind farms over a certain megawatt size to have emulated inertia. And this is response from a turbine, I'd say, E by power at the wind farm level, to a drop in grid frequency. I suppose one of the interesting things to point out here is that just before the event happens, the wind power output's falling. So if the event was to happen here, you probably would have been in a better spot. But because the wind is falling, like again, that doesn't happen in my simulations, you know, you're constant wind speed, the wind is falling, and then the inertial response kicks in, and then you have your energy recovery. But I suppose another point is that, you know, other system operators are doing stuff too, and we have Hydro-Quebec in Canada, and also PREPA, which is Puerto Rico. They have a requirement on their wind turbines. They actually have quite onerous requirements for PV panels and wind turbines. In a way, you could argue that they're being asked to do more than the generators, because they actually have to provide ancillary services to the system when the wind isn't blowing. The wind varies throughout the system, and in order to get a full handle on the potential for wind power to contribute to system stability, you need to be able to characterize how many wind turbines are online, because that's all that matters. For any sort of rotational machine to provide an inertial response, it has to be online. So for a wind turbine to be online, it has to be above its cut-in wind speed, but also because the controls will slow down the turbine to inject in power, you have to be more than you have to be above more than your cut-in wind speed. You roughly about 0.2 per unit of the wind turbine rating, so that when the machine does slow down, that it doesn't stall. So generally, inertial controls will only be implemented above a certain wind power output. So what you're looking at there in front of you is wind turbines online and above that output that's needed for an emulated inertial response. And then that's multiplied by whatever P-lim you give it. So for example, again, these parameters will define the response. Now that's only the magnitude. This shape of the response is inherent. It's not dependent on this number here, which will change from system to system and how you tune your response. I suppose you can see that when the wind power output of the system is low, you don't have many wind turbines online and above the power output that you need. Similarly, when the wind power output is very high on the system, you're pretty damn sure that most of them are online and above the wind speed that you need. Gets a bit hairier in the middle, because you know you can have lots of wind turbines online operating at a low speed, or you could have a low number of wind turbines operating at a high speed for the same system level wind power output. So you know, if you're a system operator and you're seeing this, you could take the mean of that, or this is roughly what emulated inertial response capability I could get from the wind turbines as the system wind power increases. If you're more, I suppose, some would say prudent, some would say risk averse, you could take the 5th percentile. So you're 95% guaranteed that at that wind power output, you're going to have an injection of inertial response greater than that. Of course, there's not just an injection involved with emulated inertia, there is a recovery period as well, which is probably important to characterize, because it might have a knock-on effect on your other reserve requirements if you have this draw of power.
That's because when you extract power from the wind turbine to provide the inertial response, they're taking it off optimum in terms of its energy capture capability, and so it has to go back to that.
Yeah. But also, like with a synchronous machine, that will have an energy recovery period per se, because when it gives a synchronous inertial response, it slows down to inject that energy, and then to get back to 50, when the system gets back to 50 hertz, that speeds back up. So there's give and take with every machine. But the thing with the wind is that it's decoupled from the frequency to an extent, and also there's other stuff at play, like you say, because it's hopping back to that maximum power point tracking. Very quick slide on demand response. So I'm very lucky to be working with a guy called Dr. Hassan Kazi in UCD on blending demand response control with inertial strategies, because hopefully demand response is a big player in the future because it can drive a host of efficiencies. So just a brief snapshot in that you see a base case, you have no demand response. Then we have, you can control, what we're actually looking at here is water heaters, domestic water heaters, and the intelligent control of water heaters to improve your frequency response. And then if you couple that with an inertial constraint as well, you get an improved system frequency response. I suppose the reason I throw demand response in is that it's a non-synchronous device as well, just like wind, albeit doing something else. So I suppose system operators around the world are grappling with this problem, ourselves here, but also the Electric Reliability Council of Texas. They're actually quite a leading transmission system operator. People might laugh at Texas, but they're excellent. And what I'm showing here is their suite of old ancillary services and their new ancillary services. So I suppose all I want to get you to take from here is that Texas are increasing the granularization of their services. So they're creating faster, they're creating payments for faster responses, like we are here. Finally, this is a project that has just kicked off. It's a pan-European project in Europe. Migrate the massive integration of power electronic devices. So power electronic devices, same as non-synchronous, same thing. We have Airgrid and UCD involved, and a host of other system operators. Really exciting. Conclusions. Power system inertia is reducing on both small and big systems. This is a worldwide phenomenon. There are a host of potential solutions. The point of that is to say we need to find the set of options that maintain system frequency response reliability standards, minimize carbon footprint, and is economic. And that's the challenge. Acknowledgements, I am very lucky to work with great people. So Noel Kniff in Airgrid, who I kicked off all this with. So with Noel, I'm doing the intelligent synchronous inertia scheduling. With Hassan Kazi, it's demand response. Damien is my supervisor, who gives me enough rope to hang myself every day, thankfully. Thanks very much to Paul. I send my condolences. I only heard there now about the passing in his family, which is terribly sad. Yeah, thanks very much. Paul is the one who organised this, and I'm actually really excited because in the next couple of months we're going to try and see can the electrical engineering expertise in UCD meet the policy expertise in UCC, and what can we come up with. The Irish Futures Council for putting bread on the table. These are the publications, so these are accepted, these are in the works. If you're excited or scandalised by power system inertia, send me an email. I can send you these papers because these are IEEE, so if you don't have, or CGRAE, so if you don't have membership, I'm, as lead author, I'm allowed to give them to you. If you're further excited, here's some reading, and these are some of the stuff I referenced in the paper from EnergyNet in Denmark and ERCOT in Texas, and Hydro-Quebec and stuff, NSOE, Airgrid, all the leaders in the field. Thank you very much for coming in on this fine afternoon to listen.
So we'd just like to to ask Padraig to stay at the podium, and we'll open the floor for questions. So for the benefit of the people online, if you could state your name and organisation and ask the question into the microphone so people online can hear. So, any gentleman over there.
Hello, my name is David Hughes. I'm from various organisations, but I suppose I'll say Passive House Association today. Just a couple of questions. What figure, if any, is the limit of asynchronous generation on a grid like Ireland's an island grid? I mean, what other countries would you look at in terms of achieving that are also island grids? I mean, I'm thinking of Sri Lanka and places like that. Could you just talk a little bit about asynchronous interconnections, the DC interconnectors that we have as an island, as opposed to what other grid systems have, which is AC and provides inertia?
Well, so take the latter part first. A HVDC link has power electronics on either end. It has a converter, just like PV and wind turbines. So that there is, you can control that to provide ancillary services to the grid. Just like with an offshore wind farm, it'll have a converter station onshore, and you can control the voltage with that. Same with a DC link. You can also provide, like we currently do it. We have reserve coming from both our interconnectors in the case of a contingency on the grid. So they're already actually providing stability services to the power system. I wouldn't go and build a cable to provide ancillary services given the cost of it, but the technology, what it can provide is roughly the same as an offshore wind farm or onshore wind farm for that matter. And the first one, about asynchronous limit, well, it's going to change with every power system. So in some system it might be like you will go as far until you hit your stability limit, and that could be frequency, voltage, or transient stability, and for different systems it's going to change. So I don't think it's fair to compare systems, because their mode of stability the mode that's hit first will change. Now you can fix that, and then you can push out the envelope even further, and then you'll hit another form of instability, and you'll grapple with that. I suppose what the Migrate project is actually trying to do is try to figure out 100% power electronic devices. So it's really cool. Like they're going the other way. So they're not actually trying to like the system operators. You know, they have to keep the ship going. You know, the lights have to stay on, and they have to advance the system. So you know that's nudge, 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 nudge. Whereas the Migrate project is saying, okay, scrap what we know. How would you actually operate a 100% asynchronous grid? And that gets hairy then, because frequency is no longer a concept, because we have a grid frequency, because the synchronous generators are rotating in synchronism, and they inject voltages and currents at 50 hertz. That's why we have a 50 hertz system. So if you don't have any conventional power plants, you don't have a frequency. So that's it's totally different stuff. But yeah, you're definitely not going to say it can't be done.
Yeah, thank you. This is Larry Stout from, well, I'm retired anyway, with a checkered history. Yeah, I was going to ask you, can you take it to that limit of 100%? And you've kind of answered my question. People are investigating that, because a few centuries from now, I mean, that seems to be where we're going, and it's going to be a very complex problem, but I think it's one we have to solve.
Yeah.
I'm with Donald Cassan, Gas Networks Ireland and Energy and Environment Division. Just the one question I have for you, Padraig, the level of emulated response, if you lost, thinking about it in an Irish context, if you lost the largest generator, 440 megawatts, that's a lot of small wind turbines to provide this emulated inertia, 1 or 2 megawatt wind turbines. And it sounds like, this is a mechanical engineer speaking, that sounds like a lot of, moving parts there to, to coordinate.
Well, statistically, it's actually superior, because if you're dependent on a small number of generators to respond, the likelihood of one of them not responding and the impact that would have on the system frequency is huge. Whereas if you have distributed sources, all else being equal, which is not, but if it were like that's a superior form of reserve. It can be done, and it will. So, I suppose one of the reasons I put up the demand response there is that what's going to be very important when we move forward is that we control the thing. We control our responses. So, for example, at the moment, we have demand response, but all that involves is tripping loads. Now, it gets to a point where you can't just trip the loads and forget about it. You need to control that tripping so that you move with the frequency. So I think as we move forward, we'll have to evolve as the non-synchronous penetration and demand response increase, but we're on top of it, hopefully.
Jerry Duggan, Energy and Environment Division. Thank you very much, Farrig, for a very interesting lecture. Now, a few things. One is obviously, if you want the wind turbines to behave as you indicated, you're going to have to change the control systems on all of the existing DC-DC converters on them.
Yeah.
And okay, there's a cost involved in that, and there's a multiplicity of systems involved, so that's a complication. Second thing is, EirGrid in their December publication last year seemed to be singularly unimpressed by synthetic inertia. And certainly, reading the paper, they went through a whole pile of options, and my impression of it, whether it was my misreading or their intention, was they weren't terribly interested. And we do have a significant opportunity to provide synchronous condensers in this country, in that we have a whole pile of surplus generating capacity that actually, synchronous generating capacity that actually isn't operated at all. The barrier to doing that is the actual capacity payment that these generators receive at the moment and wouldn't receive if they were doing something useful as a synchronous condenser. So I think we have to look at not just technical solutions that we've seen this evening, but also how we can actually get the best use out of existing assets, because all you have to do is decouple the turbine.
Yeah.
And that's straightforward enough. So I think system operators would be more comfortable, shall we say, with machines whose characteristics they're fairly familiar with, than relying on a box of electronics tricks that they're not quite sure will work, because they have a lot of experience with the conventional generators that in fact the frequency response is not what it's supposed to be.
Yes, in short, in that you can't just have synchronous condensers, because they'll only help with your rate of change of frequency decline. You can't form the nadir and bring the frequency back to nominal with the synchronous condenser. Synchronous condensers are great. I love synchronous condensers. If I get enough time, I'll do plenty of research on them, because they give you fault current, dynamic and steady state voltage control, and a small bit of inertia. Okay, it's not big. What else point do I want to make? I'm not sure. Can you remember the title of the document?
It was published in December the 22nd, which means it was conclusive.
Okay, so
and it's about 80 pages of fairly difficult stuff to read.
okay. What I'm guessing they were getting at, and I don't want in any way speak for the system operator, but I don't want to batter them, because I'm pretty sure that was the this is all me saying this now, if it is the Rock-Off Alternatives report. And as I've said in my presentation, emulated inertial controls is not the same stuff as synchronous inertial response. And it's the synchronous inertial response. If the Rock-Off, now if you extend that Rock-Off measurement time window, then power electronic controls can come in at the end to improve it. But currently, it's synchronous inertial response that you want to improve your rate of change of frequency. So I would guess that's what they're saying, rather than it being useless, because there's loads of good stuff that it can do, but it won't do rate of change of frequency over a short time frame.
Frank Burke from Schongrad Energy. And this is more to add to the debate and what Jerry was saying. I mean, you're right, Jerry, that EirGrid don't really regard anything like that as inertial response, certainly synchronous inertial response. And in the DS3, they have different products of different kinds of system services that they'll pay for. And in terms of synchronous inertial response, they will only pay for it if it's synchronous. We have developed a demonstration plant in the old power station plant in Road in County Offaly in conjunction with EirGrid, using flywheels and batteries to provide system services. And what they will do under the DS3 is they will pay an uplift or a multiplier on the fast frequency response payment if you can get in before the 2 seconds. So fast frequency response is from 2 seconds out to 5 seconds, and then primary operating reserve is 5 seconds out, and so on. So if you can get in half a second, they will pay you more. So they do see that there's a value, even though it's not actually synchronous inertial response. The experience that we've had to date in how we are responding to dips in system frequency is that we're responding in a fraction of a second. So it's not really synchronous inertia, but it's what we might call synthetic inertia, and it is still valuable in terms of both Rock-Off and the nadir. So I don't know what your comment on that would be. Thank you.
I suppose maybe just to close it off is that perhaps let's not worry about trying to emulate exactly what synchronous machines did, because ultimately it's the behavior of the system that we want to preserve. Now, whatever fleet of synchronous condensers and controls on renewable technologies that will keep the lights on in a low carbon, least cost manner, that's the way to go. And it's going to be a fleet of everything, including flywheels and demand response and any other inverter based technology.
So if there are any other questions, any last question? I had one for you there, Padraig, going back to your earlier slides. You had, I think, 1,500 megawatt seconds for conventional coal-fired steam plant, and then nuclear was 4,000. Why is it, I mean, they're both steam turbine technology. Why the difference?
Because the MVA of a nuclear plant is on average much higher than a coal plant. Now, in England, I'm sure there are coal plants with quite high ratings, but like in Ireland, like we're only getting up at close to 400. So in comparison to a nuke at 1,000, so that's so it's not people generally get hung up about inertial constants. It's not just your inertial constant that's important. It's the actual rated capacity of the generator as well.
Very good, thank you. So just conscious we've had Padraig on his feet there for over an hour, so I'm going to ask him to maybe take a seat and we'll wrap up proceedings. Thanks very much, Padraig. So in closing, I'd like to thank Paul for an excellent presentation. He started off by explaining system inertia to us in not too technical language. There was a few formulas there, which I'm sure gave people a few goosebumps, but it was easily understood. Certainly speaking as a mechanical engineer, I think he took the time and the effort to try and explain it to us. And I thought he explained very clearly the link between system inertia and the mechanical characteristics of the generator. He then went on to talk about his research into emulated inertia, and indeed he gave a couple of practical examples there. Hydro-Quebec, the work that they're doing and implementing these type of systems. Padraig then went on to talk about ancillary services, and he explained the link between research in electrical engineering and energy policy. So I suppose given that Padraig is a Kilkenny man, and given that their expertise in hurling is on the decline, I'm glad to see that they are getting into new areas of expertise on power system inertia. So I'd like you to show your thanks to Padraig in the usual way, please. So I'd like to thank all the attendees yourselves who came out tonight again. Lovely fine evening, and I'm sure you were glad you came along. It was a very worthwhile lecture to attend. I'd like to thank the group in Cork who are convened there in UCC in the ERI, and I'd like to ask everybody to sign the attendance sheet if it's coming around. And I'd like to welcome the new chair of the Energy and Environment Division, Des Murphy, who is taking over as of from October. So our next event will be in October, the first weekend in the first Wednesday in October. So thank you very much.